Hello everyone, so in this video I'd like to talk a little bit about optimization problems. And the idea is going to be that we start with some kind of word problem and then we turn it into a calculus problem where we have to maximize or minimize some quantity. Then we use calculus to find the maximum and minimum, and then at the end we're going to interpret that back in terms of words, in terms of the original problem we had. So it's a little bit like related rates, except instead of trying to find a rate of change, we're trying to maximize or minimize or find the dimensions that maximize or minimize some quantity we're interested in. So how should we go about doing that? Well, all the problems that we're going to see in this course are all of the same kind of flavor. So there are going to be a couple of steps. So just like with the related rates, we start by, we can't do calculus if we don't have any variables, if we don't have any symbols. So we start by assigning some symbols. If it's a complicated question, we might want to draw a diagram. Then we write a formula for the thing we're trying to maximize or minimize. So depending on the problem, it could be different things. It could be volume, it could be area, it could be cost, it could be, profit, who knows what. So we write a formula for that in terms of our variables. And then sometimes we'll get lucky and this will only have one variable, and then straight away we'll be able to differentiate and find the max or min. But sometimes there might be more than one variable floating around. So because we're doing calculus of one variable, we want to be able to simplify that. So then the next step will be to use a constraint, use the given information to write a constraint, and then use that constraint to write the thing we want to maximize or minimize in terms of only one variable. So we should have a function only of one variable, and we should have a domain on which we want to maximize or minimize. And okay, then we can use calculus. So we differentiate, we find the absolute max and absolute min, using either the closed interval method or the first derivative test that we'll talk about in a little bit. Okay, and then finally the answer, at the end we interpret the answer in terms of words, and we decide what the units are going to be, and that will be our final answer. So let's see an example of a problem where we do these kind of steps. So here is a simple problem. A farmer has 2,400 feet of fencing, and he wants to fence off a rectangular field that borders a straight river. And we need no fence along the river. What dimensions of the field have the largest area? Okay, so what are the interesting quantities? So clearly we're interested in the dimensions of the field, so we're going to need to give those names. So let those be x and y, and it makes a difference which dimension is which, right? Because one of those dimensions borders the river and one of them does not. So x and y are not necessarily the same. So let's suppose that y is the length that borders the river and x is the one that doesn't. And we're interested in the area, so let A be the area. So here is a picture. We have a very crude picture. We have a river. We have the x is the side that doesn't border the river, y is the side that does border the river. Okay, so here is our picture. Here are our variables. Next, we said we should write down a formula for the thing we're trying to maximize or minimize. Okay, so we're trying to maximize the area of a rectangular field. So it's just a product of the side lengths x times y. But then we see that this is in terms of more than one variable. So we need to find a way to write this in terms of only x or only y. So we should go back to our problem and look for a constraint. Well, we see the constraint is that there is only 2,400 feet of fencing. Okay, so we know that the total amount of fencing should be 2,400. So if we have two sides that are length x and we have one side that is length y, so we know that 2x plus y is going to be 2,400. So this is our constraint. And then we can use this to solve for y, get y in terms of x, and then everywhere in the formula for a that we had y in terms of x, we can replace it by x. Okay, so if we use that constraint, we get y equals 2,400 minus 2x. We replace the y in the formula for a by this formula. We get a is 2,400x minus 2x squared. So now we have a formula for the thing we're trying to maximize or minimize in terms of only one variable. Okay, we have to remember where are we trying to maximize or minimize this? What is the acceptable input? So what is the domain of A, in other words? Well, we have to use a non-negative amount of fencing. So x has to be non-negative. X is bigger than or equal to 0. And what is the largest possible value of x? Well, if we were to use all the fencing on the x side and none on the y side, then we would have 2x could be 2,400. So x can be at most 1,200 if we're going to use at most 2,400 feet of fencing. So x has to be non-negative and less than 1,200. Okay, so now we can forget entirely about where this problem came from. We have a problem involving calculus, maximize or minimize this function a of this closed interval 0 to 1,200. So we can use the closed interval method. So let's go ahead and do that. We differentiate and we find the critical point. Okay, so differentiating and solving for 0, the critical point is at x equals 600. And then the closed interval method would say we should compute the thing we're trying to maximize or minimize at the endpoints and at the critical point. So if we go ahead and do that, at the endpoints, the area will be 0, which makes sense because that's when either x equals 0 or y equals 0. So then if one of the side lengths is 0, clearly the area is going to be 0. And then at the critical number, if we plug in 600, we'll get A of 600 is 720,000. So the closed interval method says that the smallest of these is the minimizer and the largest of these is the maximizer. Okay, so the maximum possible area is A of 600 is 720,000. Okay, and then what we actually have to do, so in the problem, we want to know the dimensions of the field that have the largest area. So if we want to know the dimensions, that's actually asking for the xy value. So we have to be careful whether we're asked A or whether we're asked x and y. So in this case, we're asked x and y, so our final answer is going to be the dimensions that maximize the area are 600 feet and 1200 feet, and 1200 feet is the dimension that borders the river. And just as a sanity check, it makes sense that we're going to use 1200 feet on the dimension that borders the river because we kind of get the side that borders the river for free, so we don't actually have to use fencing on that. So it makes sense. So 600 by 1200. Okay, so in this example, we were finding a maximum and minimum, and it was over a closed interval, so we could use the closed interval method. What about if it was not over a closed bounded interval? Say if it was over 0 infinity, then how would we find the absolute max and absolute min? Right now, we don't have an answer. We only have a test for local max and local min using the first derivative or second derivative test. So we need one more test. So here is the first derivative test for absolute max and absolute min. So suppose we have a critical number. How do we decide if it's an absolute max or an absolute min? Okay, here are two cases where we can decide. So if for every x less than c, the derivative is positive, and for every x bigger than c, the derivative is negative, what would that mean? So that would mean until we get to c, the function is always increasing. And after c, the function is always decreasing. Okay, that would mean that f of c is the absolute max. So notice how this is different to the first derivative test for local max. If it was local max, we would say that the sign changes from plus to minus, or the sign changes from positive to negative. But then we're only caring what happens very, very close to c. And then we would only conclude that we have a local max. So here we're saying if the derivative is always positive for x less than c, meaning the function is always increasing, and the derivative is always negative for x bigger than c, meaning the function is always decreasing. So if we switch from sum to for all, then we actually get absolute max. Okay, and vice versa with absolute min. So if we're always decreasing, and then afterwards we're always increasing, that is going to be an absolute min. So here the for all x is really important. Okay, so as I said, let's compare this with the first derivative test where we just care about the change. Okay, so let's try to use this on an example. So what is the minimum vertical distance between these two parabolas? So y equals x squared plus 1 and y equals x minus x squared. So there are different vertical distances at different points x. So at x, we can find the vertical distance by subtracting. And we don't know which is the top curve and which is the bottom curve right now. So if we subtract them, we get the difference. But that difference could be positive or negative, right? If I do the top curve minus the bottom, the distance will be positive. If I do the bottom curve minus the top, I'm going to get something that's negative. So I need to take absolute values to make sure I get something positive. Okay, so at x, the vertical distance is the absolute value of the difference in the y values. The absolute value just so that we make sure we're non-negative. Okay, and now we're going to want to use calculus to maximize or minimize this, and we don't really like doing calculus with absolute values because there are places where this isn't differentiable. So we should try to get rid of the absolute values if we can. Okay, and we're looking in this example that this quadratic we got on the inside is always non-negative. So why is this always non-negative? If you think about the quadratic formula, the discriminant will be 1 squared minus 4 times 2 times 1. The discriminant will be negative. So this is never 0. And when x equals 0, the value is 1. So there is a point where the value is 1, which is positive, and it never goes through 0. So this is always going to be positive. Okay, so since the inside is always positive, we can just remove the absolute values. The height at x is 2x squared minus x plus 1. So now we are trying to minimize this function, and our domain is all x, so minus infinity to infinity. Okay, so now we turn it into a calculus problem. We differentiate, and we try to use the first derivative test for absolute max and absolute min. So there is one critical point at x equals 1 over 4 if we differentiate. And then if we test on either side, if x is bigger than a quarter, then the derivative is positive. And if x is less than a quarter, the derivative is negative. So the vertical height is decreasing until we get to 1 over 4, and then afterwards it's increasing. So that tells us that there is going to be an absolute min or a global min at x equals 1 over 4. Okay, so this is an absolute minimum. So how do we actually compute the value of h at that point? We just go back to the original formula. So there is an absolute minimum at x equals 1 over 4. The minimum vertical distance, in this case, we're asking for the output of the function, not just the input. We plug that back in, and we get h of 1 over 4 should be 7 over 8. Okay, so do be careful whether you're asked, where the absolute max or where the absolute min occurs, or what is the value of whatever we're trying to maximize or minimize at that point. Okay, so here's one last example. The steps are more or less the same, just maybe a little more complicated. So a cylindrical can is supposed to hold 1 liter, which is supposed to be 1,000 centimeters cubed of oil. Find the dimensions that minimize the cost of metal to manufacture the can. So what are the interesting quantities here? So it's a cylindrical can, so we can specify exactly a cylindrical can using the radius of the circular cross-section and the height of the can. So we're going to be interested in R is the radius, H is the height, and then we're trying to minimize the cost of metal, okay, which is going to be proportional to the surface area. So we're going to want to minimize the surface area of the can. So these are our different symbols. You might want to draw a picture, but I was too lazy to make a picture, but you can imagine a cylindrical can. Okay, so we want to minimize the surface area, we said. So if you imagine a cylindrical can, if you're kind of soda or whatever you have, then there are two types of surface area. There's some surface area on the top and the bottom, and then there is a surface area around the sides. And each of the surface areas on the top and the bottom, each of those is a circle. So on each of those, we're going to get pi r squared on the top, pi r squared on the bottom. So we get this 2 pi r squared. This corresponds to the surface area on the top and the bottom. And then the surface area around the sides is 2 pi rh. So we have two terms for the surface area. We get 2 pi r squared plus 2 pi rh. And then clearly, this is in terms of more than one variable, so we need to write a constraint and then use that constraint to eliminate one of the variables. And that constraint is that the can is supposed to hold 1,000 centimeters cubed of oil. Okay, so using the formula for the volume is pi r squared h. We know that pi r squared h has to be 1,000. So we should solve for the simpler variable. In this case, we can solve for h in terms of pi and r squared, because we don't want to take square roots. So h is going to be 1,000 divided by pi r squared. And if you trust me to plug in, we can get the area is going to be, the surface area is 2 pi r squared, which is unchanged. And then the second piece in terms of r becomes 2,000 divided by r. Okay, and then the only restriction is that the radius should be positive, because whatever radius we have, we can always play around with the height in order to make the volume 1,000. Okay, so we want to minimize this function of r with domain 0 to infinity. So now we have a calculus problem. So let's differentiate. If we differentiate, we get first term 4 pi r. Here we have 2,000 out of the minus 1. We get minus 2,000 out of the minus 2. So minus 2,000 divided by r squared. Okay, and since we're going to be interested in, what is the sign and where are the zeros, I want to factorize that. So if we find a common denominator, here should be r squared, I'm sorry. So if you have 4 divided by r squared, we get pi r cubed minus 500. So we can see straight away that this is going to be 0 if pi r cubed equals 500, r cubed equals 500 divided by pi. R is the cube root of 500 divided by pi. Okay, so kind of a mess, but whatever, here is the solution. And is this an absolute max or an absolute min? Because we are really looking for the absolute min. Okay, if r is bigger than this value, the derivative is positive. And if r is less than this value, the derivative is negative if we go back to the formula. So that means we're decreasing until we get to this value, and then afterwards we're increasing. Okay, this is going to be an absolute min. So this really is the absolute min by the first derivative test for absolute max and min. Okay, and then we were asked to find the dimensions, right? The dimensions that minimize the total cost of metal, or the surface area. So the dimensions are r and h. We already know r. We have to find h. Luckily, we have a formula for h in terms of r. So if you go back and plug your minimizing r back into this formula for h, we're going to get the corresponding height is h equals whatever this number is, 2 times 500 divided by pi all to the cube root. Okay, so these are the optimal dimensions. Okay, so that about wraps it up. So just remember, what are the steps? We're given a word problem. Introduce some notation, maybe draw a picture if it's helpful. Write a formula for the thing you want to maximize or minimize. Use a constraint to write that in terms of only one variable. Decide what your domain is. Then use calculus to find the max and the min, or max or min, depending on the problem. And then at the end, interpret in terms of the original problem and make sure you answer the question you were asked. Okay, that's it for today. Thanks, everyone. Stay safe and see you next time.